Dear participants, and when you are listening of the lecture, if you have any doubts, write down on the paper. After completion of the talk, then you can ask easily. So time saving also. Thank you very much.
All right, should we continue? So, because was a question about examples to delineate these classes of mappings, this is a very nice monograph, and you'll find all kind of examples to show which is different. So, it's a book, Iterative Methods for Fixed Point Approximation. This is the name of the publisher. Cluj-Napoca is in Romania, 2009. And if you need a soft copy, I can provide it. Maybe I thought to give you my email address, but maybe better I'll send to Professor Murthy, both the book by Ruth, this monograph, big monograph, and this one, and you can read. So this is full of examples, you will be satisfied with them. So let's go back to all right, so I just want to indicate how a new idea can be put in value, can be developed. I did myself just a few. I left to other young people, and there are at least some hundred of papers that use this almost construction as a starting point, and there are many papers. I did not have seen all, I did not see all of them. All the time I said, oh, I should have a look on them, but I don't find time. So the first important development was to go from single-valued mappings to multi-valued. So we introduced, together with my co-author, Madalina, this important paper on a general class of multi-valued weakly Picaro mappings, which was published in Journal of Mathematical Analysis and Applications. And after that, this was the condition. And if you are not familiar with the Hausdorff-Pompeiu metric, this is the distance between sets. This definition has been done in 2 steps. Pompeiu was a Romanian mathematician. He introduced this distance in complex plane. He was doing his in the complex plane, so in R2, let's say, to introduce the notion of convergence of sets, of curves, actually. The sets in the complex plane were curves. He was doing geometry. And he introduced the notion of convergence of these curves, and he introduced this in his PhD thesis in Paris. He did in France, his PhD. Then, Hausdorff, he has a great German mathematician. He wrote a monograph this year, and he discussed in more detail this distance between sets. So this is the Pompeiu-Hausdorff or Hausdorff-Pompeiu metric on the class of closed bounded sets, parts of X. So we are in a metric space, and the condition for multi-valued almost contraction is quite similar to the single-valued case. We have this H distance between Tx is a set, Ty is a set, and fixed point for a multi-valued, if you are not familiar, means X belongs to Tx, because Tx is a set. And these kind of multi-valued mappings are very important in applications. There were mentioned this important contribution by John Nash in economics, which are based on topological fixed point theorem, actually, not metrical fixed point theorem. And a group of Indian mathematicians, as I know, are from Andhra University, because Babu was, it was organized some years ago, a conference in his honor, and he invited me to speak. It was online. I don't know them in person, because at that time it was online. He wrote a paper, and instead of this condition, instead of the original condition for almost contraction, he used this. And this is a very interesting contribution, because if you remind, here in the original condition of almost contraction, we have L times dy Tx. And he put this minimum, and what is interesting, this condition includes both existence and uniqueness of the fixed point. So such a mapping in the single valued case includes both existence and uniqueness by including these four distances. And Madalina Păcurar in this paper this is in 2008, and in 2010 she showed that this condition is equivalent to the existence and uniqueness condition together. So this is the case, multi-valued case, I consider together with them. And here is the paper in 2007, and we can read together the theorem. The theorem, it's a very general one, but not the most general. So we have a complete metric space, T. It's a multi-valued delta L almost contraction in the sense I mentioned. This means there exists theta less than 1 and L positive, non-negative, such that we have this condition. And then we have existence, not uniqueness, and approximation result regarding the approximation of fixed points by an orbit. In that case, this sequence is constructed by taking xn plus 1 in the set T of xn. So all the time the sequence in this case is constructed in this way. So it's a kind of selection. And for this sequence, we have also, this is the a priori error estimate. We have first two points, x0 and x1, and this is called a posteriori error estimate. Why? This is very important in application. I'll have some application later in this week, but I want to take this opportunity to show you what is important this second error estimate. So we have the fixed point. We want to calculate it. We know that distance between xn and u, xn it's a sequence, is less than this h. H is not given here, but it's a number, something with theta. I do not remember now. And what does it mean? We want to approximate this in such a way that dxn u is less than epsilon. Epsilon is the error, the admissible error. So it's simple. We put here epsilon, and then we find that we'll stop our iteration algorithm when we have this inequality. Which is this? So what are we doing? We start with x0, we compute x1. We compute the distance is less than 1, we are done. Now we continue. Distance between x2 and x1 is satisfying this inequality, is done. And so on, we stop our process, let's say, at this step when this inequality is true. So this is very important from the point of application. Someone asked here, why is it important? Because in concrete examples, we have to compute this fixed point with a certain precision. So in order to have sure this precision, then we'll use this error estimate, a posteriori. A posteriori, it's a Latin. Latin is an antique language and means afterwards. And a priori means before. So we know afterwards, after doing some iteration, when to stop. And this is a priori because doing the same, doing hn 1 minus h dx0 x1 less than epsilon, then we got information about n. N will be greater than. Here we use logarithm, and then we'll get that we need to do n, let's say 100. This means we need 100 iterations. So we know from the beginning how many iterations to perform in order to get this approximation. And in the other case, we know just afterwards, after we compute the iterations. Okay, this is the record of interest for this paper. We can see more than 200 citations in Web of Science, more than 2003 in Scopus, and more than 300 in the Google Scholar. So a very interesting paper. A lot of people use this condition. And I shall end with some other developments. I have shown you before some contraction conditions arising from Banach condition. Among them is the Chirich condition. I write once again it, because this is very important. dxy, dx dx, dy dy, dx dy, and dx dy tx. This is the most general condition in the Rhodes classification of contractive condition. I mentioned this paper 1977. And what was my thought? Let's compare almost contraction conditions, which is this one I write again. To Chirich condition, I said which one is more general. Of course, it was interesting to compare. I succeeded to find examples, and in this book I indicated there are examples to show that there are almost contractions which are not Chirich, and there are Chirich which are not almost contraction. That means they are, and there are mappings which are in both classes. So we are here. Almost contraction, Chirich contraction, and we have this situation. So my plan was, is it possible to unify this? This means to obtain a class which will include almost contractions and Chirich contraction because they are different. This would be similar how was done by Chirich-Reich rules when they unified Banach contractions and Cannon contractions. So they unified this. And I tried to do this. I said, okay, we'll have this. Instead of d of x, y, we put this quantity, which appears in Chirich contraction condition. And in this paper, General Constructive Fixing Points, I established some fixing point theorems. By chance, Chirich was asked to make a review. And he wrote me personally, I think there is something wrong in the proof. I feel it is not. So please read again, check the proof. It happens. You will see, it happens sometimes we are quite sure the proof is correct from the beginning to the end, but sometimes one step, one argument is not solid, is not valid. So the same happened here. And the problem was coming from these two to deal with such a condition. You have seen an idea how to prove Zamfirescu fixing point theorem. The problem was when the maximum is this or the maximum is this. So there was the problem. There was needed another condition because such a mapping with M here does not have always a fixed point. This was the problem. So it was the case, and I construct a very nice example, a simple example. This is important to mention. So we take what I said. Examples are fundamental. So we should prove that our results are effective, our results are real generalizations. So in the end, after several trials, I found this example. So it is easy to see that we define this map on the set of positive integers, non-negative integers, and in this way, this map is fixed point free, because n plus 1 equal n will be 1 equals 0, this is false, so no fixed point. But what is interesting, this map, it's a Chirich almost contraction. A Chirich almost contraction means we put m here, and the rest, the others remain the same. And, okay, all the computations with alpha 1 over 2, L2, we can show this condition with m here is satisfied, but the map is fixed point free. So the theorem here, the main result here, is not correct. So I improved it, I corrected it, and the only way it is functioning is to put, instead of them, they are not good for the proof, so, but they are average. I'll speak next days about the role of average in mathematics. Average, what does it mean? We have something not very good, something very good, and if we do the average, what it results, it's quite good. And there was a famous Romanian mathematician, he did a joke with his students. The students did not understand the concept of average or mean. We say sometimes mean. Oh, she said, you don't understand what it means in mathematics, an average, a mean. He said, look, if you sit with this part of the body on a very hot machine, and with this side on ice, in the average it will be fine. This is the idea with the average. So the average is solving the problem. So if we put average of these two bad cases, then we get the result. And the result has been published in the same journal 1 year later, and this I called Chirich strong, because this condition with mi and 1 implies the condition with m. So I called strong Chirich. And I told in the break, during the break, to Professor Murti, I was in Belgrade, in Serbia. Chirich was in Belgrade. This is in Serbia. On the map with Romania, Serbia has a common border with Romania. Very good mathematicians in fixed point theory are there. And I was in Belgrade just to speak about Chirich almost contraction, because it was a tribute to him. He was very kind to say, look at the proof. This proof should have something. Okay. Now let's continue. All these results we discussed so far are for mappings which have this property we call self mappings. Self. But in applications, for example, if you want to apply a fixed point theorem to differential equations, it happens often we have to show how we deal with a differential equation. I wanted to show you some application to differential equation, to partial differential equation I published, but it was not placed in these lectures. So we have a differential equation, let's say initial value problem, and we know it is equivalent to a fixed point problem where t is an operator. And this operator is defined on a set, but it maps D in the whole space X. We have to prove that T of D actually has this property. This is a self-map. This means T is a self-map. But in many cases, we do not have this property. So in that case, we are put in the position to solve problems for non-self mappings. So we have to deal with such an application which does not fulfill this condition. And this is the case with non-self. I succeeded together with my collaborator, Madalina Păcurar, to treat this case, which is very, very interesting. And unfortunately, we published it, look, more than 10 years ago. We planned to have some applications, but we did not succeed. But because of the time. What is the fixed point theorem for non-self almost contraction? So we can work not in a metric space, but in a Banach space. We need linear structure of the space. You know, Banach fixed point theorem has been stated in a Banach space, in what we call now Banach space, because Banach did not call this space Banach. Afterwards, people called after his name. So we have a Banach space X. K is a non-empty closed subset of X, and T is a non-self almost contraction, means T is mapping the set K into the whole space X. And we know that we have this condition for almost contractions. If we introduce this property M comes from monotony. Because my co-author initial is M, some people ask, is coming from her name, and is not coming from her name, is coming from monotony. And this property is very important, because there is, in the proof, there is a similar case to the previous result I mentioned, and this is the property. I have one example, but I'll show you later this example on the slide. So this is the space X, this is the set K. So what happens for X is here, and property M, means that if we have such an X with Tx outside K, then we know that there is a Y here, the point on the border, the point with this property, not this one, sorry, because it should be in this way Y. There is such a point, such that Ty, it could be here, the distance between Y and Ty should be less than the distance between X and Tx. This is property M, and I'll show you a better example, a better draw. And secondly, if we have this condition, Rothe boundary condition, what does it mean? That the border, it's always mapped into K. So this means that any point from the border, this is why I put Ty here, because always points are mapped here. So all the time from the border we go inside. So in that case, we have the conclusion that T has a fixed point. If we are, as I mentioned, in the case of integral operator, Tx, this is a very strong tool for us, because we could solve differential equations or integral equations which do not satisfy these conditions. So we have, okay, I use K. T of K not included in K. We have this case covered. So this is the situation. So this is the set, this is the space X. This is the set K. And I took an X, and Tx is outside. And the requirement to have property M is that we should find amongst these points on the border, we have 3 in this case, at least one that distance between y and ty is less than tx and less than distance between x and tx. And this is property M. And because I insist to have always, when we establish or we pretend to be established a new result, we should provide an illustrative example to show our result, our extension, our generalization is effective. And this is the result. It is really nice. So we have here K is the real axis with the usual norm. K is the interval 0, 1, and T is this map. And you can see we are inside 0, 1 on this branch. We are inside of 0 on the interval 0, 1 on this branch, but we are outside at the middle of the interval of 0, 1. So we can check that this map is a non-self almost contractions with these constants. Look, 8. So I mentioned that an almost contraction is in general, in that case, we have greater than 1, while all the other fixed point theorems have less or at most equal to 1, is Hardy-Rogers fixed point theorem. And T satisfies property M. How? The border of this K, the border is 0 and 1, right? The point 0, 1. X1 over 2 is in K, but Tx is outside. So here it's 1 over 2. And okay, I cannot draw here is -1 somewhere. And the distance between between 0 and T of 0, which is, this is y, is 0 and is less than distance between over 2, 1 over 2 and -1, which is 3 over 2. So the property M is satisfied, and the Rothes boundary condition, I forgot to put here, we can check T of 0 is in our set K, and T of 1 is in our set K. So also Rothes boundary condition is satisfied. So we are done. This is a true generalization of other special. Now the last topic for today, it's just to give an idea on enriched almost contraction. I'll speak about enriched mappings in a separate lecture, but here I just want to show how we can continue to develop our new results. So in a paper which is not put here, I introduced the concept of enriched contraction. I'll give you very many details on this technique, maybe tomorrow or the day after tomorrow. I introduced the notion of enriched non-expansive mapping, but here I speak about enriched almost contraction. And what is this? we have a linear norm space. A mapping is an enriched almost contraction. If we can find a B, non-negative constant, a theta in this interval depending on B, and a positive, non-negative constant L, such that we have this inequality for all x and y. You can see immediately that if we take B equals 0, this term disappears, and we get exactly almost contractions, because this also disappears, B0. So these are almost contraction, but if we have L equals 0, we get enriched contraction, we get other classes of enriched enriched mappings that we studied. Sorry, this was published 1 year before, but I forgot to put the new situation. And this is an enriched contraction in Banach spaces, which is devoted to enriched Banach contractions, and this is enriched Canaan in the third paper. This is how we could develop. And here it's again, let's speak once again. So we have almost contraction are here, and we introduced enriched almost contraction. And these are almost contraction. We pretend that this class is larger, but we have to prove. So we have to find here an object which is not here. And then we are done. So this means this set of mappings enriched almost contractions is larger than almost contraction. And then this means we have a benefit. We progressed in our work. By the way, because it was mentioned in the opening, maybe I'll have time to speak. Such a class of mappings I called unsaturated. This means we can enrich it. And if we cannot, if this class would be exactly the same, it will be saturated. This is another concept. I do hope I'll have time to speak. So this is the example. In that paper, we take X, this interval with the usual norm, and we define T in this way. So two branches, 1 minus 6 and 2 minus 6. It is immediately to see that 1 over 2 is a fixed point, because 1 over 2 will give this, and 1 is also, again, here, 2 minus 1 is a fixed point. So we have two fixed points. This is an enriched almost contraction for any theta in 0, 2, because B is 1, this is B. B is 1, theta is in the interval 0, B plus 1, and L is 3. And if someone wants to see this paper, I'll indicate later the exact paper. But this is not an almost contraction. We just show because it does not satisfy the almost contraction condition. Is not in any other class of enriched mappings I mentioned, and maybe I'll speak next days, is neither non-expansive nor quasi-non-expansive, is not enriched non-expansive, and so on. And this is indeed is not even enriched Chatterjee, then it is a very general class. So if these are almost contraction, look, Here are Banach. Here is Cannon. Here is Chatterjee. Here it's Zamfirescu includes all. There is Chirich, Strong, and so on. All are included here, and this class is overall. So it's comprising all these classes of mappings. I close with some other important developments. There is a very nice extension of this result. Tomonari Suzuki is a Japanese mathematician, and he succeeded to give result for Banach type contractions to show that they characterize the completeness of the matrix. So he published another paper and called these mappings almost contraction. He called Berinde mappings, and he succeeded to show that this constant I put here L can be a function of y. Very nice is his result, and he provided also an example showing that this class of almost contractions is more general than the usual almost contraction. There are many other developments. I don't insist on them, just to know that some other authors considered this kind of mappings even for non-expansive mappings on various kind of sets. Here is the group led by Sutep Swantai from Chiang Mai in Thailand. And many others, I don't insist on them. Just a few conclusions I would like to present. So, I discovered almost contractions searching for a proof. So this is very important. Sometimes I encourage my students to take a theorem and to look at its assumptions, to not look in any book how to prove it. Just to put in the left-hand side the assumptions, in the right-hand side the conclusion or the conclusions, and to try to find a bridge between them. And sometimes, if you are doing this, you should find new interesting results. I draw your attention on this name, Caristi. Professor Kamsi from USA, now he is in Emirates, will give a similar GIAN course in February in Aligarh. And he will speak about Caristi fixed point theorems. Caristi did such an approach. He used to be PhD student of this great mathematician, William Ard Kirk. And Kirk posed him the following question. Take Banach contraction principle and try to prove it in another way, not using the usual way Banach did by considering the sequence of successive approximations and prove that this sequence is Cauchy, is fundamental, then in a complete metric space is it convergent, then let's see X star its limit, and we prove then that the limit is a fixed point. So he tried another version, and he introduced what is called now Caristi mapping. It's a more general version. It also includes, so here is Banach contraction principle, and here is Caristi. Okay, all the time I was thinking almost contractions are somehow here also. I had no time to, it's a challenge for you. I had no time to discuss what is common with Caristi and almost contraction and what is not. This proof is very nice of Caristi. By the way, Caristi, I know this story from an American mathematician. He left mathematics and he was very disappointed because he realized his theorem is very important. He submitted to a journal, and a great mathematician, I don't mention his name, he died. He was the reviewer. He realized this, it's a very important step. He realized it's a very important step. He was already a very famous mathematician. And he took the idea and he moved aside, I'll tell you, and proved a very important variational principle and published the paper before Caristi. Caristi's paper waited, I don't know, 2 or 3 years, and it was published after this paper, and this was really bad, really unfair thing, and Caristi left mathematics forever. He left mathematics, and as I know for this friend of mine from USA, he succeeded to contact Caristi. He was working, he was so disappointed because of that. He did some, how to say, psychological breakdown, and he was working in a farm, like a farmer, for a long time. And this mathematician, he succeeded to contact Caristi. This is an example of unfairness, unfortunately. Okay, so this is in connection to Caristi. Sometimes it is good to try to do this. So for any of these theorems, just try to see how another way, if possible, because sometimes we cannot see how to do. So, as I mentioned, I call this class of mappings weak contractions, and then I realized that there exist weak contractions, and in spite of the fact it includes a lot of contractive conditions I mentioned then, this condition is singular in the sense it ensures only existence and not uniqueness, and it is not a Picard mapping in the sense I mentioned, so it is a weakly Picard mention. So if we compare the theorem, fixed point theorem for almost contraction to Banach contraction principle, we see that the uniqueness is lost, but please look at the theorem I presented for almost contraction. All the others are present in the theorem from Banach contraction, except uniqueness. So this is its beautifulness. It's almost Banach contraction because it's how I said, it's a union of an infinite number or finite number of Banach contractions. And almost contractions have applications. Maybe I'll have time to present an application to functional equations. For non-self almost contractions, there are many interesting open problems. If someone is interested, should go to the original paper and consider developing in many other directions. Also, the idea of Suzuki with this L being not a constant but a function of y is also a possible research direction, very promising in my opinion. Okay, non-expensive mappings have in common something with this, and some people, you can see here, endpoints, this is generalized wherein the non-expensive mappings is related to almost contractions, but with this delta equal 1. So with non-expansive term there. And last, I want to cite, to quote from Suzuki. Suzuki, who is a very, I do respect his results, he said that the concept of almost contraction has some mathematical beauty. So sometimes you ask, some of you ask about applications. Sometimes mathematics is done for its beautifulness. If we should have a look in the current mathematical research, we can say without any chance to be wrong that 80% is theoretical, pure research. We don't know exactly tomorrow what application will have these results, but I'm sure one day they will have an application. Maybe I'll tell you at the one of my lectures with applications about this very famous Fermat theorem in number theory. People at that time, another French mathematician, you should know about his name, Fourier. Fourier said, oh, these kind of results about number theory are not important for application. And nowadays, number theory is essential in cryptography. It's fundamental. All secrets are based on number theory. So sometimes it takes hundreds of years to find applications, sometimes sooner. I'm confident all these concepts in fixed point theory, but we have to work on it. We have to find application. I just heard in Delhi and Ghaziabad about applications of fixed point theory in machine learning. People are starting to work. I did myself some applications with some of my PhD students in image processing. There are many applications. I close. This is me 20 years ago, 21 actually. Can you believe? This means 20 years. So you can see here a piece of paper. At the moment, it was during the summer. This is a wooden house in the country. I have a summer house for spending time there in holidays. And with my wife, you have seen her now, and my two daughters, I knew at that moment this is an important concept. So here is distance between tx and ty less than alpha dx and y plus dy tx l. So exactly the condition. This is a historical picture. I love my daughter had the idea to make this picture 21 years ago. So this is almost contraction. Lot of work can be done related to this class of mappings. Just follow some of the indication I gave you. So we have to take a paper to read not in diagonal. By the way, when we grade papers for exam entrance to the university, I have a colleague of mine the same age. And always we grade in diagonal. Do you know what is in diagonal? Just have a look. Not noting this is 0.5 points. In the end, said this is 7 or 7.5. And when we meet together, we discuss what is your grade to this paper. 7.5. 7.5, exactly on diagonal. We do not read a paper in diagonal. We should work with pencil and paper. We read any concept. We go to its definition. We go to see some related concepts, some related results, and be sure we understood all. This is what I tell to my students at this course, methodology of research. This is the way I applied almost always to when I read a paper carefully, then I found something to improve. I believe this. It was one mathematician, Romanian mathematician, he had no citations. His paper, no citations. This was 8 years ago, more than 8 years, very famous. And he was unhappy with this. And another mathematician, a colleague of him, said, no, your manner of writing a paper is wrong. You treat the problem completely. Please leave a small place for young people to go from there, a starting point. And he did this. So sometimes there are papers which are complete. So no chance to, but my belief is that in any paper, any result, always is it possible to make a connection or many connections to take all together and to find something, a new way to conduct research work. So maybe I should stop here. If you have questions, put them now, please.
Hello. Anybody have questions regarding of this session?
If not, we can put next days.
Otherwise, you can note it also before starting the afternoon session. You can ask personally also if you have no.
This is not a conference, once again, as Professor Murthy said. It's an interactive course, interactive workshop. So you should ask any kind of question you think are important for you.
So you can note it out, if you have any questions, and you can ask after completion of this lunch break, and you can ask personally also. Otherwise, at any time of within the 5 days pattern. So I would like to pause our program for 1 hour. Working lunch is providing the besides of this room, and please go on take the lunch break. And after we will meet at 2 o'clock. Please be ready to meet here again, same place.